All right, why don't we get started? All right, well, as you see, there is a test coming up. It's also on the, it's been on the lecture page for a while. And in answer to the inevitable question, what's going to be on the test, I will give my inevitable answer, the famous Hilfinger answer. You are responsible for the sum total of human knowledge from the beginning of recorded history, with particular emphasis on the content of this course. In other words, no, I don't tell you what's going to be on the test. Expect us to be reasonable. And I know I'm being old-fashioned because this is the way that things were in my day. But and I know we've moved on to modern times. But what can I say? I'm an old stick in the mud. All right, so the project is due next week. The TAs will be meeting with you, I hope, your teams, to find out, first of all, to make sure that you're actually working on this and to find out how you're doing. Those of you who haven't started or aren't on a team, time's a wasting. You're almost too late, so for heaven's sakes, get that straightened out and get working on this. All right, so questions, administrative or otherwise, project questions, anything like that before we start, because we're getting on to into a new unit of the course. No, really? Huh. So how does this work? The people who don't have questions come to lecture, and the people who do have questions stay home? Oh, I see. It's all on Piazza. Okay. No. That's nice. All right, there was one little omission from the reference manual. I hadn't noticed it until someone pointed out, which is that, yes, a plain expression can be a statement. Without that, things go wrong. And a couple of people have answered. We've already seen an interesting question of getting grammars to work, grammar hacking, which is that you may have noticed that some people were asking this question. Let's see if I can quickly reconstruct with the particular issue. If we might. So you're trying to say something like, as I recall, it's something like, well, let's look at the form. So this had to do with what programs look like. So let's imagine that we have a grammar in which we have a program which is either a head followed by a tail, and the head is either is some sort of a declaration. I'm sorry, the head is either empty, let's say empty, or it's a list of things, and the tail is either empty or it's a tail list. And the problem is that head lists and tail lists can both start with the same entity. So a head list is some sort of head item, or a head list followed by a head item. A tail list likewise. What? I'd love to know how I do that. It just happens sometimes. I'm never quite sure what strange combination. So it's a tail item or a tail list followed by a tail item. looks harmless enough unless head item and tail item can start with the same thing. And then you see the problem, which is if you see that thing that either a head item or a tail item can start with, you don't know whether to take this reduction here, or the parser doesn't know, whether to take this reduction here or to go on and start accumulating a head. It doesn't know that until it gets further into that first item, head item or tail item, whatever is at the beginning. And so the problem is to figure out a different way of writing the same grammar so that you get the same effect. And remember, the advantage of LR parsing is supposed to be that you can decide to do a reduction after you've seen more than you would see with LR1. So basically, even though this is intended as an LR1 grammar, it's sort of been forced into a mode where it has to act like LR1, because basically it has to make a decision right here, right at the very beginning of a program, for example, about whether or not to reduce head list to empty, even before it's seen whether it's got a head item or a tail item. Now, someone noticed that if I take off this option for head, then all of a sudden it becomes, or maybe it's, yeah, if I take off that action for head, I think it is, this will suddenly become doable, even if head item and tail item can start with the same thing. And you might ask yourself, why? What is the difference that causes that to happen? So anyway, this is a useful little puzzle. I'm not going to post an answer, because I think that in working through this, you'll gain a better understanding of what's involved in parsing, or what's involved under the hood in parsing, as well as picking up a couple of tricks that you can use for alternative ways of writing grammars. So it'll be an interesting exercise, I think. All right, does that suggest any other questions? All right, well, in that case, let's get started. All right, so we've done lexical analysis with its nice little tools that you can use for that purpose, and context-free parsing with its tools. So far we are getting something that will produce trees. There are other things it can produce, but in our case it's producing trees. It's eliminating any of the parsing, the compiler errors, the parsing errors, the syntax errors, so that we know that these trees are well-formed. They are well-formed formulas, WOFs, as they are sometimes called. And they are, therefore, the later parts of the compiler don't have to worry about that anymore. It's all taken care of. So at this point, it's time to continue and now do some more analysis, and to do the things that you can't do with context-free parsing. Now, understand that if we're thinking just about, even if we think just about recognizing a language, is this a correct Chakapai program? Even when you're thinking about that, this division that we have into lexical analysis, parsing, semantic analysis, is in a certain broad sense kind of arbitrary. In fact, the division lines that we have are largely to fit the tools that we've got. There's a convenient way of defining everything up through the context-free syntax, because we have tools for that. So we separate the context-free syntax from the rest. But in some sense, these are all languages And the whole thing is a language, and the entire Python, an entire Chocopi or Python program is I think we can get away with a type 1 language, as it's called, which is, it's the step above, it's the step after context-free. And the way I describe this is we're going to take this context-free tree, this abstract syntax tree, and we're going to decorate it in various ways. We're going to add some information that can be used by the later parts of the compiler, and at the same time will eliminate certain errors. Now, there were a few exercises in the homework that addressed what it is that you can't do in the context-free language. So the main thing that we cannot do in a context-free language is that we can't perform checks. You can't describe checks such as this identifier has been declared, or this identifier is declared somewhere in the program, or the identifier that's used in this statement is used someplace else in the program. And the reason for that is basically, if we just go down here, take another non-context-free, non-CFG. And if we take a look at a grammar that is not context-free, the grammar describing this set, so the set of all words, so all W's, let's say identifiers, followed by something, followed by identifier, all strings of this form where the two identifiers are equal. There is no context-free language that defines that set. The two IDs are two identical identifiers. And if you can't do that, then obviously you're not going to be able to do any of the more complicated stuff, like making sure that everything is declared and has the right type and so forth. So already, even with something really simple like this, you can't do it with a context-free language. Now, you may recall you can do ID something, ID in reverse, but that's not very helpful. Right? That's not very helpful. So what we do is we punt. The context-free syntax gives us a superset of the valid programs, and then we winnow it down further in the later stages. So that's the deal here. And we also add extra information that isn't really represented, isn't easily represented in the tree form in the first place. So first, a little terminology. You hear me use these terms static and dynamic a lot. I've been using them since CS61B, or for that matter, since CS61A, to refer to their descriptors of different kinds of properties. So static refers to properties that can be inferred from the text of the program without reference to anything else. So, for example, in Python, you know that this X and this X refer to the same thing. And you can tell that from the program. It doesn't matter. The data don't matter. The particular execution of the program doesn't matter. It is always the case that this X and this X will refer to the same thing. So the parameter to the function, the thing you call the function with, will be the same thing that X refers to here. On the other hand, a dynamic property is something that does depend upon the actual execution, an actual execution of the program. It cannot be inferred from the program itself. It's determined by an actual execution. For example, is this a valid division, or does it cause a divide by zero error? You can't tell, because it depends on what happens when you execute the program, what value y takes on, or values that y takes on. Now, this is not as obvious as it seems. For example, in principle, statically, we can determine from this program that x and y have the same value. So from that, we could write a little program, something like this. Let's just take a look over here. We could write a program that looks like this. X equals, here, what was that example? 3. All right, so x equals 3, y equals x plus 2. If y equals 5, or if y is greater than 5, then z equals x divided by 0. Now you can tell statically that this is not going to cause a divide by 0 error, right? Because you know that y is in fact going to be equal to 5, not greater than 5. Therefore, you know this will never be executed. And you can tell this regardless of, this is always going to be true. You can tell this from just the text of the program. I don't have to execute the program to find out this is true. So, one could say that the non-zero divisibility by 0 is a static property of this program. Now, and since static semantics, or what I'm calling static semantics, is generally concerned with the static properties of the program, you might say, well, so this is something that we could do during static semantic analysis of the program. It's true, it is something you can sometimes do. The problem, however, is that if we generalize this, and we have, for example, a program up here or a portion of a program up here that does an arbitrary computation whose result is in principle predictable, and then we have some test of it, like down there. It is possible to formulate this in such a way so that if you have a compiler that could actually detect these things, you would have a compiler that would solve the halting problem. It would solve an undecidable problem, or an uncomputable problem, which of course is impossible. So the problem is that along this path, if you go far enough down this path, you get to the point where you've got impossible tasks. You're asking the compiler to do impossible things. So, being engineers, what do? Well, we say, okay, in that case, we're going to go only so far in what we call static properties, and then we're going to stop. Now, as it turns out, when you get into the real world, and especially into the real world of research, you find that, in fact, there are people all over the place who are very interested in more powerful static properties of programs than the things we're going to be doing in this course, who are interested in things like, is this value ever going to be 0? Is this value ever going to be null in general settings? And in fact, one application is in certain areas of software, such as what are called safety critical systems. For example, the avionics of an airplane or an aircraft. These days there are aircraft, many of them, that basically can't be flown without the aid of a computer, for the most part. And of course, so system failures in that case are, shall we say, rather critical. And certain organizations, most notably the FAA, are kind of paranoid about making sure that you're, before they certify a plane, that in fact the software on it is going to be safe. So there is and of course, one could imagine testing all the possible things that might go wrong with an airplane might take quite some time and be rather dangerous. So in that particular area, there's a great deal of interest in expanding what is meant by static analysis, so that it includes a great deal that we're not going to deal with in this course. It's a fascinating subject, actually, with a long history, but and we'll get a little flavor of it, but we can't go very far down that path before our compiler becomes very complicated. So that's not what we're going to be doing this semester. So what does the semantic analyzer do? First of all, it's one task is to link up declarations of things with their uses. So you know, for example, that we can have an identifier that actually means several different things in different parts of the program. For example, a local variable with a name like I tends to get used all over the place, meaning, and it refers in each case to a different I. So linking those things up is part of the things that static semantics might do, as well as, in fact, making sure that each identifier instance is declared somewhere. It's possible that you might want to reorganize the AST a little bit into a more convenient form when you discover certain things. For example, it might be that you'd like to distinguish between function calls that are actually method calls and function calls that are something else. For example, in Python, if you, quote, call, unquote, a class, you get it's basically like new in Java. And perhaps you might want to change the semantics you might want to change the tree to indicate this, possibly. That's one way to do it. So that's something you might do. And then, of course, you want to detect errors and fix and allow further processing. Oh, and I skipped the very big one, which is determine the static types of expressions. Make sure that the types of everything are consistent. So you get certain typical errors that you find that you've probably all run into at some point or another. Declaring a variable more than once. Failing to declare a variable. Declaring a variable whose type does not match how it's used, so that at execution time you would get a nonsensical result if it were allowed to continue. Or a sort of a subset of the subset of the first place of the previous one, which is you have a function call where the number of parameters is wrong, or the parameter types are wrong, or something like that. And then some more exotic ones. In Java, there was built into the language for the first time. I don't know that I've seen this happen very often before, but built into the language for about the first time was this definite assignment check. So if you see a message that says error, such and such a variable may not have been assigned at the time that it's used, that's the result of failing the definite assignment check in Java, which does a conservative check, a static conservative check that you will have assigned to each scalar variable, each individual variable, before you actually use it. That, by the way, is a very interesting example of what I was talking about before. So, for example, if you have a program like this, say like this, maybe. And you say something along the lines of int y, and then print y plus x, Java will complain. It will say, hey, you didn't initialize y before you used it. Now, if you read the manual, it also says that y does have an initial value, a default initial value, which is 0. But in the case of local variables, you're not allowed to do this. You're not allowed to do what I have here. On the other hand, if I change this program, well, in this case, too, I have not initialized y2. I've initialized y, but I haven't initialized y sub 2 officially. So you could imagine that this program, you might want to complain about this. But in this case, there is no complaint. And instead, we just use the default value of y, which is 0. Everything's fine. And the reason for that is that this 2 here, in general, in the general case, would be some sort of an expression. So there'd be some sort of computation to get 2. And in order to know whether, and in order to figure out whether, in fact, you had chosen an element of the array that had been assigned to, you'd have to do, you'd again have to solve the halting problem. You'd have to solve an undecidable problem in the general case. In a simple case like this, you can figure it out just by eyeballing it, but in the general case, your poor compiler wouldn't know what to do. And that's because there has to be a computation to see what this is. So it could adopt a very conservative rule, which says that you can't, that after initializing an array, you have to go through, you have to have a for loop that has a certain form that initializes each element or something. But that got to be very annoying. So the implementers satisfied themselves with just checking that you don't get simple variables, that you've always assigned simple variables before you start. Okay, so that's an interesting little aside, I think. At least I think it's interesting. So what are we going to get out of this analysis? Yes? I don't quite know what you meant by your first statement.
Well, so all of the languages we call them Python languages.
Yes.
Languages sort of describe programs that try and determine anything about their algorithms.
Yeah, type 1 and type 0. Well, type 0 is the more general one, yes.
But if anything recognized as a finite state automaton, then like any language, which could be higher language to be like a finite state automaton, you can program things that would sort of result in
Well, that's not true because, and it's not true for a trivial reason, which is that one of the things you could do in such a language is write a particular arbitrary program. You know, I mean, any even regular languages can produce as their output any particular finite set of programs, and I can write one program that is not whose validity is not determinable, and so by that token, the fact that something can be generated or recognized by a language, that a language can be generated or recognized by a finite state machine does not necessarily mean that that all the static properties can be determined computationally. Yes, yeah. It's about additional properties of the program. All right, so what I'm imagining, what we can think abstractly is coming out of this is that we start with our little tree over here, and then we attach to it in red a little bit of extra information. So, for example, here I've attached to each identifier a reference over here to an item over here that gives that gives information about this identifier. such as its type and how far down, how many functions it's nested inside. So this identifier here, number 1, is not nested inside any function. It's Python. We're talking, if this is a Python program, which is what this is, then its type, the type that you can assign to X can be any type. And then there are other parts of the program, like, for example, this integer 3, its type is int. So we know that. I mean, we can tell that its type is int statically. So we attach this information to the tree, and that's basically the idea. So that's sort of my abstract picture of what's going on. Now, how exactly you do this, whether these are fields or you get at them some other way, that's another question. So I'm going to call these things over here symbol entries for the time being. As you can see, you can't tell very much in Python. Simple variables can have any type. A function, an f, like this, has maps something of some type, any type, to some other type. I've said that the result of x plus y is any because in Python it can be an integer, it can be a string, it can be a list, and you're also allowed to extend, you're also allowed to create new types that have pluses on them. So it gets so in Python there's not a great deal you can do. You can say statically. All right, so this is basically the idea. We've added symbol entries, they hold this information, and that is in the abstract what we're going to be doing with static semantic analysis. Now, ChocoPy, we can be much more specific because this is this language has a stronger type system. So here, for example, this is not the syntax we're using. I've just done something that's sufficiently compact that I can stick it onto this slide. So we have, for example, a variable declaration that containing, which is basically attributed, so x : stir. So this tells us now that that x will be this entity whose type is stir and whose nesting level is 0. So now we can be much more specific. Hi has type stir, 2 has type int, and so forth. And this plus we can now say returns an integer because we know that when you add we can tell that x is of type integer, y is of type integer, and when you add those two, you get an integer. So our trees will have more of this information, although again, the particular representation is an entirely different matter. Now, what about classes? What happens when you define a class? What do you get? Well, in Python, we can do some pretty weird stuff, which makes static analysis of any type problematic. We can do scope analysis. That is, we can tell what thing X refers to much of the time. But consider this example. I now have a class with a single method that returns self.x. I've defined, this is a perfectly legal Python definition, even though x is not, as you can see, there's no x defined in A. And I can then create x. I can this assignment here, a1.x equals 3, will suddenly cause the object x to get a new field. The object pointed to by a1 to get a new field called x, to which I assign 3. And I could call f at this point, and everything would work. On the other hand, if I try to say print a2.x, having created another a called a2, or if I called f on a2, if I said a2.f, there would be an error at execution time because the field x is not defined. There is no x attribute. Whereas in Java, we're much more, or C++, or and similar languages. This program itself is illegal, even if you leave off this thing down here, which would cause an error. Why? Well, because Java's static semantics conservatively require that any attribute you mention, any attribute of an A that you mention, has to be declared explicitly in A. It can't be added after the fact to individual objects. So the idea is, presumably in a statically typed language, the symbol entry for a class, say for A, would contain a list of would contain some sort of list of the members and their types, as because those things are, because that's information you need to know whether a call, like a reference like this, a1.x, is valid or not. Now, a little bit more terminology. And here I have to admit that I am somewhat at odds with the community, or some parts of the community. First of all, the scope of a declaration is the section of text or program execution in which a certain declaration applies. So you will sometimes see people refer to the scope of X. Naughty. Doesn't make sense. The only thing that makes sense is talking about the scope of a particular declaration of X, because X itself could refer to different things at different parts of the program. So the scope of a declaration is that area of the program where it makes sense. So, for example, if you have a function and you define a local variable inside it, the scope of that local variable declaration is the function body. That's the way in Java or Python, for example, or C. And I'll use another term, declarative region, to refer to a section of text that forms the that limits how big the scope of certain things can be. So, for example, a function, the declarative region associated with the function definition might well be the body of the function, or something that starts at the particular the body of a function. So that would limit any scope within there. And then we say that if the scope of a declaration is determined entirely by where it appears in the text of the program, then we say the language is statically scoped, because a compiler could determine what anything means just by looking at the text of the program. And if, on the other hand, you can't tell what the scope of a declaration is until execution time, then we say the language is dynamically scoped. So a bit more on that later. Now, we can define, in just about any language you can imagine, there's a possibility of using the same name for different things. And this is generally, and there are generally rules about when this is okay. So, for example, things that are declared in two different declarative regions are okay. If there are also examples where things that involve different kinds of names, different kinds of things, may be declared in the same place. Perhaps you've noticed this in Java. So in Java, it's possible to have two things with exactly the same name and having overlapping scopes. Who can think of an example? Have you encountered anything? Something that's two different things, same name, overlapping scopes. Yes? Yeah, well, in those cases, you've got, your example is you have an instance variable and an argument of a method. But in those cases, those two appear in two different declarative regions. One of them appears in the region enclosing that's the class body, and the other one is in the function body. Now, I'm interested in something that's more where they can appear in the same region. Yes. Okay, that's one example, but anything else? Think for a moment about a constructor. So how do constructors work in Java? We have the name of a class, and then the same name is used to define a constructor. So we have class, array list, blah, blah, blah. And inside there's something called public array list, blah, 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 which is its constructor. So you have two different names. Their scopes sort of overlap. And the question is, how does Java get away with that? Why doesn't that cause confusion? I'm asking you to think about the design of a language that you already know. Have you ever thought about that? Why doesn't it cause confusion? Yeah, why doesn't it cause confusion? Yeah, but if I say array list, how does it know that I'm talking about the class as opposed to the constructor? Yes. So, for example, could you be more specific? Depends on how you use it. Right. So if I'm using it in the context array list blah 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 of array list blah 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 x, I know that I'm referring to the class. If I say new something, then I know that I'm referring. Well, actually, in that case, I'm referring to both the class and separately to the constructor. So I'm referring to sort of both of them. Another example is how about this sort of thing in Java. So I'll have a class A or class F, say, and int F. There's actually no conflict there, interestingly enough. It looks like there ought to be a conflict, but there isn't a conflict. Because when you use it, if I say F space X, then I know, oh, this is the class F. If I say F dot something, then then it depends, but it means something else. I can have class name. I can have methods that have the same name as instance variables. And then, of course, I can have a constructor. And then, of course, I can have a constructor. Pretty weird, but there you go. Okay, so now, there is always this question about what happens when you use two things with the same name. What happens? So, the sort of default that everybody uses is and refines is the Algol scope rule, which is that when you have multiple declarations that might apply to something, you take the innermost, the smallest declarative region, the innermost region that declares the thing, and that's the one that applies, right? And anything else, and it hides or shadows definitions in anything else. So that's sort of the default rule. But then there are variations on this. So Java and other languages like Clue, for example, said, well, it's kind of confusing when you do that, because one typical error is you use, say, I as a parameter, and you also use it as a control variable in a for, and you get confused as to which is when you're looking at I, which one is it are you referring to? So methodologically, we'll just say that you can't do that. You can't shadow a local variable with a local variable of the same name, or a parameter with a local variable of the same name. These are just variations possible within a language. And then, of course, we can define what the declarative regions are. So in Java, a curly begins and ends declarative region. That's sort of the big one. And so each function body is a declarative region. What else is a declarative region in Java? So function bodies are anything else? Yeah. Yeah, you can put one smack dab in the middle of when you can say if blah blah blah, curly brace int I, blah blah blah, and curly brace, and then so int I, and then in another place you have curly brace string I, blah blah blah, and curly brace. As long as they aren't nested inside each other, that's perfectly legal. Confusing maybe, but perfectly legal. And those are two different declarative regions, and therefore things don't overlap. Whereas Python has different rules. It's become somewhat less. Well, I don't know. Python 3 made some modifications because I think they sort of thought they went too far in Python 2. So in Python 3, they realized, well, since we don't have variable declarations, instead assignments to variables sort of double as their declarations. We have a slight problem with, for example, if statements and for statements because, if statements in particular, because if you assign inside a branch of an if, say the then part of an if, is that supposed to be a declaration of a variable or what? No. If it's a declaration, and where does the scope of that declaration end? If you then say that it ends as it would in Java at the end of the then part. So if you have a Java with a then part enclosed in squigglies, any variable you declare in there goes away when you leave. If you did that in Python, you wouldn't be able to assign to variables inside an if statement and have it work outside and have that same variable work outside. So Python says that in a program like this, there's only one x. So this x up here, the parameter, this assignment to x, this x in the for loop, they're all the same. They all refer to the same x. And in fact, we will print 5 here, even though we're outside the for loop and x was 3 to begin with. Now, Python 3 said, hey, when we have generators and things like that, like for lists and sets and dictionaries, list comprehensions and generators, then the x will not leak out, the x after the for will not leak outside. It will be part of its own declarative region there. But for for loops, it's all part of the big declarative region here. So as you can see, there's a lot of variation that you can have in these languages. It's all part of but they're all the same concept, just slightly differently defined for each individual language. Okay, we'll stop here and we'll take this up on Wednesday.